After familiarizing ourselves with the nature of polarized light in my previous movie clip, let us now examine the design of CD spectroscopy and the principle that gives rise to a CD spectrum. A CD spectrometer consists of three main components: a light source, a sample held in a cuvette, and a detector with a recording system. First, light source. Unlike UV visible absorption spectroscopy, which uses non-polarized light, CD spectroscopy uses circularly polarized light. To generate circularly polarized light, the light source in a CD spectrometer is typically a xenon arc lamp. This lamp produces intense, continuous radiation from about 160 to 900 nanometers, covering the far UV region, which is important for protein secondary structure analysis, as well as the near UV and visible regions. Because the radiation emitted from a xenon arc lamp consists of non-polarized light with continuous wavelengths from 160 to 900 nanometers, a monochromator is used to filter out the unwanted wavelengths. In addition, because the radiation emitted from a xenon arc lamp contains non-polarized electric fields, a CD spectrometer also includes a circular polarizer. Method of generating circularly polarized light. Circular polarizer consists of two optical components, linear polarizer, and a quarter wave plate. To generate circularly polarized light, a linear polarizer is placed at a 45 degrees angle with respect to the y-axis, as shown. When non-polarized light passes through a linear polarizer, it becomes linearly polarized light whose polarization axis is oriented at a 45 degrees angle to the y-axis. The emerging linearly polarized light can also be expressed as the resultant of its x and y components, as shown in the equation below. When linearly polarized light with x and y components passes through a quarter wave plate whose optic axis is oriented along the x direction, the plate affects the x and y components differently. Because the x component of the electric field is aligned with the optic axis has no effect on the propagation of the x component of the electric field. However, because the y component of the electric field is perpendicular to the optic axis, its propagation is delayed by the optic axis. The optic axis delays the phase of the y component of the electric field by 1/4 of a wavelength. Thus, when the x component and the y component, delayed by 1/4 of a wavelength, re-emerge and combine, the resultant wave becomes circularly polarized light. Therefore, when left circularly polarized light of a defined wavelength passes through a sample and its energy matches the delta, electrons in the molecules absorb the energy and are promoted to an excited state. The different wavelengths absorbed by the molecule can be detected and recorded. Similarly, when right circularly polarized light of the appropriate energy passes through the sample, the wavelengths absorbed by the molecules can also be recorded. Unlike UV visible absorption spectroscopy, CD measures the difference in the absorption of left and right circularly polarized light. By convention, the y-axis of a CD spectrum represents the difference in absorption between left and right circularly polarized light. Structurally symmetric molecules, such as coronene, absorb left and right circularly polarized light equally. Thus, the difference between the absorption of left and right circularly polarized light is 0 at all wavelengths. In contrast, structurally asymmetric molecules, such as hexahelicene, absorb left and right circularly polarized light unequally, producing a CD spectrum. Thus, the CD spectrum of any molecule with an asymmetric structure can be recorded. CD spectroscopy is widely used in the analysis of biomolecules and macromolecules. Many biomolecules, including amino acids, carbohydrates, proteins, and DNA, possess asymmetric structures. For example, amino acids exist as two enantiomeric forms, L and D, and helices found in proteins are typically right-handed. The most common form of DNA, bDNA, is a right-handed helix.
you.